Welcome to the Evolution of Congestion Management in Fiber Channel webinar, presented by the SNIA Data Networking and Storage Forum. My name is Erik Smith, and I'll be your host and moderator for today's webinar. And I'm pleased to introduce you to our expert speakers. Howard Johnson, Principal Engineer working for Broadcom-Brocade, and he's also the Chair of Insights Fiber Channel. Harsha Bharadwaj, Distinguished Engineer, DC Switching Business Unit for Cisco. Dale Kaisner, Principal Architect from Broadcom ECD, also Emulex. And Scott Rowlands, Technical Staff Software Engineer from Dell Technologies with the PowerMax organization. Before we get into the presentation, a little bit about SNIA. SNIA is an industry organization that develops global standards and delivers education on all technologies related to data. SNIA is comprised of 200 industry-leading organizations, 2,500 active contributing members, and over 50,000 participating IT end users and technologists worldwide. The SNIA Data Networking and Storage Forum, or DNSF, is an active group within SNIA that provides vendor-neutral education and insights that are intended to drive the awareness and adoption of a broad set of technologies, including storage protocols, AI, and implementations. We do this by providing expert webinars, white papers, blogs, and presentations at various industry events. Some logistics for today. You are welcome to ask questions during the presentation by selecting the Ask Question option and entering your question, and we will either answer that question verbally during the presentation or afterward in a Q&A blog post. Now, if you're looking for the slides, they can be found via the Attachment tab at the bottom of your BrightTalk console. Let's take a quick look at the SNIA legal notice. This provides SNIA's copyright notice regarding the use of material. SNIA is not providing any legal advice, and there are no warranties expressed or implied, so if you want to reference this material, please do so at your own risk. Now, today's session will start with Howard providing an overview of fabric notifications, including some of the details in the FC specifications that define how they are used. He'll also walk us through a classic congestion scenario. Next, we'll discuss implementations and considerations, with Harsha providing details about the fabric and how each type of congestion event can be detected and reported using fabric notifications. This will be followed by Dale discussing how an HBA implementation might respond to receiving a fabric notification. And finally, Scott will discuss how fabric notifications might be reported by a storage array implementation and potential remediation steps that could be used. And with that, I'll turn it over to Howard.
Thank you, Erik. I want to thank also the DNSF for the opportunity to present this new technology developed by the Fiber Channel community. What I'd like to do today is provide you with a sense of the fabric notifications architecture. What we'll start with is a description of the problem set, basically what led us to developing the standards and the architecture associated with fabric notifications. We'll go through the solution scope, and then we'll talk a little bit about the Fiber Channel standards activity associated with bringing this technology to the marketplace. We'll also cover a bit of the architectural overview to describe how fabric notifications works, and then we'll wrap it up with a description of a congestion scenario that is addressed by the addition of the fabric notifications technology. The biggest problem that the Fiber Channel community has been dealing with over the last decade or so are persistent intermittent errors. The products within the Fiber Channel ecosystem have evolved to address many of these issues in various different ways. A lot of the persistent intermittent error type issues tend to be significant customer escalations. They're hard to find, they're difficult to isolate, and it takes a lot of manpower to both figure out what's going on, figure out where it is, and then mitigate the problem. A lot of the causes associated with these issues are marginal cables, marginal FSPs, bad connections, and things of that sort. In addition, congestion issues can crop up in environments that make it difficult for applications to deal with that in an automated fashion. Oftentimes, administrators are required to evaluate the situation and make manual interventions to deal with the problem. When these problems occur, which are never when you're ready for them, they tend to have a significant impact on the environment that's where these issues occur. One of the cool things about the fiber channel community is that the solutions in products has evolved and matured to the point now where there are tools that can be leveraged by simple additions to the architecture that can help us alleviate these problems. The other reason that we're trying to deal with this particular issue is the performance impact these kinds of problems have on customer environments. Oftentimes, when a simple SFP failure is causing intermittent problems, the applications can see a near zero performance impact. That is because the logical characteristics of the applications are trying to determine at a much higher level what is happening to the paths associated with the target and initiator products. To deal with this, the fiber channel community came up with fabric notifications, which is a combination of software-based notifications and hardware-based signals. When a path is determined to be impaired, the tools within the environment can detect that issue and then use the notification to tell the upper layer applications what's going on. In this case, the example here that you see on the right, we have a multi-path solution that has two paths to storage. One of the paths have been impacted and it's been detected by the switch in SAN A. The switch will tell the server that there has been a problem on the link between the switch and the storage. That server can elevate that notification up to the multipath layer, who can then make an explicit decision about what to do. In this case, it can indicate that that path has been degraded and then use alternate paths to drive the I/O. This allows the system to automatically isolate and mitigate the problem and maintain the performance of the application. In congestion situations, signals can also be used between two endpoints of a link to indicate that there are resources being consumed to a threshold, and then indicate that to the other end of the link, which will then take a mitigating action. The fiber channel community began working on this particular problem in late December of 2018, and then completed the specifications by April or early 2022. Interestingly enough, however, solutions became available in late 2020, which is kind of an indication that oftentimes the process of standardization tends to lag the process of innovation. The completed standards have just been wrapped up and have been made available to the ANSI Standards Organization for publication. The draft standards that originally indicated the architecture for the fabric notifications feature are found in the framing and signaling standard, the link services standard, and the switch fabric standard. The architecture defines two things. It defines a software-based FPIN, a fabric performance impact notification, which is an extended link service. That one is defined in the Fiber Channel Link Services Revision 5 standard. And there are the hardware-based congestion signal primitives. These are defined as a simple primitive signal, which is a character that can be sent between two endpoints of a link. The characters have both a warning and alarm characteristic. And those primitives are defined in the Framing and Signaling Standard, Revision 6. The fabric notifications provides a mechanism for identifying link integrity issues. That is, I've got a marginal cable and I want to let an upper layer application know that I have a marginal cable. When that is detected, the detecting device sends that notification to the fabric controller, who then determines how to distribute that notification. Notifications are distributed based upon the characteristics of the configuration. That is, which devices are zoned with the attached device that is affected by the impairment, and which devices have registered to receive those notifications. In the case of a congestion condition, the detecting device can provide a notification to the congesting device, that is, the device that's causing the congestion condition to exist. And it can also send a peer notification to devices that it is zoned with to let them know, hey, there's a device that you are zoned with that is experiencing a severe congestion condition. And then lastly, delivery notifications can also be presented in the event that the fabric has to discard a command. And that allows the sending device to actually circumvent or short circuit the normal timeout scenarios associated with a SCSI command. Congestion signals are defined between two endpoints, and the endpoints exchange information about what level that they support. That is, will the transmitter support both the warning and alarm signal, and at what frequency can it transmit it? The receiver exchanges information indicating which signals it supports, warning or alarm, and at what frequency it can receive them. This allows the two sides to agree upon a frequency for sending congestion signals, so that when resources at the transmitter reach a particular threshold, it can then start transmitting the signal to indicate to the receiver, hey, I've got frames for you, and I need to send them or they'll be discarded. The receiving device can then take a mitigating action to deal with the backup of frames at the transmitter. Now let's take a look at a congestion scenario where fabric notifications comes into play. In this particular example, we have a classic core edge environment where the devices are at the edge switches, and they're about to start up their particular day with host one doing a backup from the remote storage over on the right, the blue storage. Once it starts its backup activity, that fills the link, and he's quite happy because he's receiving all the data that he wants. If both the storage and the initiator are running at the same speed, then the frames are being consumed by the host at the same rate they're being transmitted by the storage. If, however, the storage is a bit faster, then this particular path is going to become full. That is, it's going to back up with frames. However, host one is quite happy because he's consuming frames as quickly as he can, and he's doing the job that he's been asked to do. Then all of a sudden, another application comes alive on host one, and he asks for his data that's on the purple storage. And now this path, the AB path, from the core to the edge, becomes full with both the purple storage traffic and the blue storage traffic. Unless the host is twice as fast as both the blue and purple storage, frames will begin to back up on both of these paths. In this case, host one is still probably not indicating that there is a problem, even though the AB path is completely full or congested. It's not until host number two comes alive, and he's trying to just do a simple production operation, getting his data from the purple storage. Unfortunately, the purple storage is unable to send data to host two because he lacks credit to send frames to his attached switch. So now the data that's being requested at host two is being throttled by the activity that's over on host one. As you can see, this is quite difficult kind of problem for a system administrator to resolve or even observe. Basically, what happens is the customer, that is the administrator or the application administrator on host two, just says, hey, the purple storage is broken. You better call that storage administrator, and by the way, get the vendor online. Now, if we add fabric notifications into this environment, instead what we see is that once host one becomes congested, we immediately send an FPIN notification to that host. It can then automatically take a mitigating action, such as reducing the rate at which it asks for data to a point that allows more conducive flow throughout the fabric. We can also send a peer notification to both the purple storage and the blue storage to let them know that, hey, host number one is oversubscribed. You may want to pace the data that you're sending to it. Using these notifications, the storage can back off a bit and speed match the host request, and the host can also change the rate at which it requests data. This automated mitigation system allows the system administrators to deal with the configuration issue, which is the applications on host 1 trying to get both at local and remote data simultaneously, and then mitigate that at some other time. These notifications can be surfaced in some type of application that allows the administrator to see what's going on, but the automated responses allow that mitigation action to be taken place at a time and place that's much more convenient for the system administrators. In the meantime, host 1 has changed its behavior and has allowed the fabric to function as it is currently designed, and host 2 becomes happy because he's able to get his data upon request. And with that, I'm going to hand things over to Harsha.
Just before we jump into Harsha, sorry, there's one question. The slide states that MPIO solutions struggle with resolution. Can you offer an explanation why better software implementations did not become widely available?
Oh, certainly. That's a very good question, Erik. The MPIO solutions are dealing with feedback at a logical level. That is, they're using I/O to determine that there's a particular error. For example, when an I/O starts up, if it's not able to complete, it times out. The only thing that the MPIO solution can do is try to test that path with another form of I/O, such as a test unit ready or some type of innocuous command. Typically what happens is the MPIO solution sees that he's gotten a timeout on a particular path. He marks the path as marginal, does a health test on it, maybe a couple health tests. Because these are small, usually 1 or 2 frame type operations, they often pass. He then marks the path as being active again and starts using it. It's not until I/O ramps up on it that we begin to hit that intermittent problem, such as a flaky SFP who occasionally causes a CRC issue. And then the cycle repeats itself. And then you end up with this one particular path that goes from marginal to active and marginal to active. You kind of see a sawtooth type behavior. That particular problem is endemic to any of the type of algorithms, such as least time, queue depth, or active-active, or active standby type of algorithms are typically deployed in MPIO solutions. By giving it either the signal or the notification, it now has an explicit notification that says, you know what, retrying that path is probably just going to cause you heartburn. So why don't you use the other paths? So now it has that explicit information to be able to deal with the problem.
Thanks, Howard. Go ahead, Harsha.
Okay. Okay. So Howard gave a good overview of the Fabric notification. So what I'm going to do is cover the Fabric portion of it, meaning how do you map the Fabric notifications into the Fabric? How does the Fabric deal with it? How does it notify end devices? So first things first, Fabrics provide this service, but the end devices, which is basically host and storage, need to register for this service. So the registration for this service is offered by 2 ELSs. For congestion signals, we use the EDC ELS. EDC stands for Exchange Diagnostic Capabilities, where the host or the storage comes and informs its capabilities with respect to signals, with respect to severity levels, frequency, etc. And the switch in return returns its severity, frequency, RxTX capabilities, etc. And then they come to they negotiate and come to at least capable values which become operational on that link. Similarly, for FPIN, RDF ELS is used. RDF stands for Register Diagnostic Function, where the end device comes and specifies what are the type of FPINs that it's interested in receiving, and the switch gives an accept specifying what are all the types that it is capable of supporting. Once the host or storage registers this information, it's persisted on the switch in a database, and that database is used to notify the signals or the FPIN as and when events occur in the fabric. The host or storage devices can decide to choose to register for FPIN or congestion signals or both, because it depends on what kind of information, what details of the information they are looking at. So they can decide to register for both or one of them. And in case the switch does not support any of these features, or it's disabled on the switch would reject these particular ELSs. Switches also support monitoring policies. I mean, both switch vendors have been supporting this for some time. And this is a policy configuration where you specify what are the type of events that you need to monitor. And in this particular case, it could be congestion events, link integrity events, etc. You also specify thresholds for each event. In this example, it could be a warning threshold or an alarm threshold. You also specify the frequency with which you need to monitor, right? And also the actions that you need to take when the threshold is crossed for that particular event. And in this particular case, your action could be sending the FPIN notifications or sending the congestion signals. And once you have this policy has to be enforced on the switch. It could be a group of ports of the switch or the entire switch, or using an orchestrator or a fabric manager, you could potentially enforce it across the fabric. The switch vendors have default policies which are defined, which are pre-activated, which should be good for most situations. But there could be some special situations where vendors may want to, rather customers may want to change either the frequency or the threshold, or some of these parameters, in which case they may want to choose a non-default policy, in which case configuration has to be done by consulting the switch vendor documentation. Let's do a bit deep dive into the congestion piece. So switch ports experience two main types of congestion. One is credit stall and one is oversubscription. And the root cause for all these congestion events is end device behaviors, right? Host or storage behaviors. And that's essentially because switches on its own do not generate any traffic. Traffic always originates from endpoints. And if the traffic coming from one of these endpoints is not is not conformant to the rules of the fabric, because the fabric is no drop, the fabric ends up holding on to these traffic, and that's when you start seeing congestion. So congestion always originates at the switch F port, and if the congestion persists for long durations, it ends up even congesting the E ports, creating victim devices. So when I say victim devices, it means devices which had nothing to do with the congestion, but still got impacted by the congestion in the fabric. So fabric congestion was dealt with by vendor-specific solutions till now. One popular example is the congestion isolation into quarantine VLs, where congestion traffics were put on separate VLs. There were two problems with this. One is obviously it was vendor specific, and the second problem was the switches were trying to mitigate the problem, whereas the root cause was the end devices. So FPIN and Signal solve both these problems. These are standard notifications, which means vendors implement it in a uniform manner. And also it puts the congestion mitigation responsibility back on the end device and relieves the switch of that burden of handling congestion. So FPIN and Signals are doing roughly the same kind of functionality, but what they differ in is the scope and the information that they give. FPIN is the scope of FPIN not only goes to the congestion causing device, but also to its zoned peer devices. And the information it carries is also much more in terms of what type of event, who is the detecting port, who is the attached port, etc. Signals are the scope of signals is only to the congestion causing device, and also the information it carries is very minimal, just indicates that the congestion is present or not present. And once an end device receives FPIN or congestion signals, they are expected to take mitigation actions, typically some kind of IO throttling. And my co-presenters later will delve more into these aspects. And once a congestion is relieved, FPIN has a specific notification type, which says congestion cleared. And in case of congestion signals, just the action absence of congestion signals means that the congestion is relieved. Let's look at the credit stall congestion and how the switches detect it. Now, as we all know, fiber channel is a no-drop fabric, and it is achieved by doing buffer-to-buffer crediting on the link. And the way it works is, in this case, I'm just showing an example of an F port and N port. The N port has a bunch of receive buffers, and these receive buffers translate into transmit credit on the F port side. And as and when these buffers are consumed, meaning the frame is dequeued from those buffers, it's returned as a credit back to the transmitting port, and frames keep flowing with this crediting logic. Now, if the N port happens to slow down, which means the buffers are not dequeued in time, it also delays the returns of credit back to the transmit side, which means the transmit credit count goes closer to zero, and eventually can hit a zero credit condition. And once that happens, the transmit queue on the F port basically stalls. It cannot transmit any more frames, and that's when you have congestion spreading inside the fabric. The switches detect this using two conditions. One is the transmit credit B2B counter going to zero on the F port, and the second condition is the transmit queues stall for lack of credits for transmission. And if this exceeds a certain threshold time interval, that's when we declare that this port is experiencing credit stall. And the switch monitoring policy that's enabled by default on the switches would track this on all the F ports with the action of generating F pin or signals or potentially both. The second type of congestion is oversubscription. This happens when the port receives more traffic than the bandwidth that it has, right? So if that is the case, then whatever is the residual traffic ends up being held on the switches, because fiber channel is a no-drop fabric. And this can happen due to multiple reasons. One, it could be speed mismatch devices communicating, one-to-one traffic patterns, or a host doing a lot of I/O, right? For example, it's doing a high IOPS or throughput. An example here is a 1 MB read. If happens at 3.5K IOPS, it can put the response of that can potentially saturate a 32 gig port. So you can do the math on that to figure how that happens. So the root cause here is different than credit stall, but the side effect that the fabric sees is essentially same, which is back pressure and congestion spreading. And oversubscription is one of the most common types of congestion we see today in FC fabrics. And the switches detect this based on two conditions. One is the TX data rate, which is the data rate of the port is very high, example, an 80% or a 90% threshold. So that in itself is not a problem because the links are supposed to operate at 100% capacity without any problem. But in addition to that, if there is also a buffer buildup on the switches, or there is a high latency that packets are experiencing, again, this would be highly dependent on the switch architecture. Which means essentially back pressure is building up on the fabric for the traffic destined to a link that is already operating at a very high throughput. So if that happens, we declare that port to be oversubscribed. And the switch monitoring policy by default tracks this on all the F ports with the action of generating F pin or signals or both. The final anomaly that the switch detects is link integrity. So as already Howard talked about, faulty links is very bad for I/O performance. Faulty links can happen due to bad SFPs, cables, or hardware that causes packet drops and truncated packets. So all these situations will result in IOs not completing, initiators or targets aborting IOs, causing IOs to be retried, and all this means lower performance due to higher IO completion latency. Now switches detect all these types of problems using hardware counters. There are a bunch of counters I have listed here, like link loss, sync loss, invalid CRC, uncorrectable FEC errors. So all these are different counters that the switch maintains on a per port basis. And the mitigation action for this, again, lies on the end device. wherein they take some action of bypassing these links using the multipath drivers. Again, my co-presenters will talk more about this later in the presentation. And this is what causes the FPIN link integrity events to be sent out from the switches. The switch monitoring policy, again, by default, will track these events. And this is tracked on all the ports across E ports and F ports, because you want to be known of the end devices should know of any faulty links anywhere in the fabric. And the action for this is to generate FPIN. Finally, let us look at how all these things come together in a workflow kind of a fashion. So I have a simple example here of two switches connected to each other, and there are devices connected to each of them. Switch 1 has H1, T1 as local devices connected to it. Switch 2, which is remote as far as switch 1 is concerned, also has devices locally attached, but becomes remote devices H2, T2 to switch 1. And these devices come and register into the switch with EDC and RDF saying their intention for subscribing to these FPIN and signals. The same happens on switch 2 as well. And on switch 1, we have an active monitoring policy that's actively looking for events of interest. And whenever that event triggers for that particular threshold, the policy rule will trigger information about that event with respect to the type, level, who on which port it happened, and things like that. So this information is sent to the local device registration database, where we see which are the devices that are interested in receiving these events, and those events are sent to those particular registered devices. So what is sent is essentially FPIN congestion notification and congestion signals. Now, in addition, there is also a need to send peer congestion notifications and link integrity notifications, which has to pass through the zoning filter, where the information is passed to the active zoning database, and all the devices that are locally zoned with the device where the event happened is also notified about link integrity events or the peer congestion events. Now, in addition to that, the domain controller of switch 1 also sends a remote notification using SWFPIN to the domain controller on switch 2, where a similar thing happens, where again the information is filtered through the local device registration database and the active zoning database to determine which are the end devices that needs to be notified of this FPIN link integrity and FPIN peer congestion notification for an event that happened on switch 1. So this way, information propagates through all the end devices connected to the fabric, and they take actions as appropriate. So with that, I complete the fabric part of notifications. With that, I hand over to Dale from Broadcom, who will talk about the host view of fabric notifications.
Thank you, Harsha. So to talk specifically about the hosts and the HBAs in that, as Harsha and Howard have pointed out, the fabric is really the best place to detect congestion events, because that's where those events are seen and notifications can be issued. On the flip side, the hosts or the HBAs are the best place to manage that activity, because the host is the device that's requesting or writing data across the fabric. So when we look at the HBAs and look at the FPIN notifications and signals that are available to us, there's really three actions that can be taken. The first action would be taking direct action in relation to a notification or a signal that comes. And that example would be active congestion management. So if there is an event that is creating congestion, the HBA could actively take action to help mitigate that congestion. The second action that an HBA could take would be forwarding that alert or that notification up to an OS layer for action. As Howard has indicated, the link integrity alerts going up to the MPIO driver would be an example of the type of action that could be taken by the higher layer inside the OS. So the HBA would pass that information up to the MPIO layer. And then the third action that could be taken is simply logging in alerts. And so one example of that could be a peer notification event where that information comes in and it is logged, and maybe even an alert sent to the admin to let them know that there are activities going on in the fabric that may need some attention. So taking the congestion example, we can see here that we have on the right-hand side of the screen a server that has a collection of VMs on it. And in this scenario, what may have occurred is that additional VMs were added to this server, creating a load that's larger than the server can handle. At that point in time, the server is continuing to ask for data across the fabric, but is not able to process that data as quickly as it is requesting it. And of course, the challenge with that is the impact, as you can see on the servers to the left, the impact is seen elsewhere on the fabric. So suddenly other devices on the fabric are now experiencing traffic issues, and the device that's causing the traffic issues is unaware of that scenario. And this is where the FPIN CN, the congestion notification or signal, comes in. So the switch can now send a signal to that specific port or ports on the fabric to indicate that that is specifically where the issue is coming from. And at that point in time, the HBA then can take action. And historically, if this had been the case where there was an HBA port that was overloaded, the historic reaction for that might have been to change the queue depth. By changing the queue depth, you would change the amount of requests that are outstanding, and ultimately, by continuing to reduce that, you would reach a point where you are no longer creating congestion on the fabric. Today, with the HBAs that are out there, the more modern HBAs, that activity can be automated, and a more adaptable active congestion management can take place. And what I'm showing here on the lower part of the slide in the center is the overutilized host running at a very high rate of speed. And this would be an example of something that we demonstrate out of our labs. And down below that, you can see some impacted hosts that are also running at a reduced level, but still running seemingly at a steady state. And then with the vertical line in the center is an example of when that alert is received by the congesting server. And at that point in time, the HBA has taken action and it's changed the IO profile. So what is happening here is that the HBA is now that port is that HBA is aware that that port is creating congestion, is changing the IO profile on that port. And that means that the bandwidth may be going down slightly, that maybe the rate of which things are being requested across the fabric is changing, but the HBA can make decisions based on the IO coming out of that HBA, can make decisions to alter that IO profile. And what you see with the graph at the center of the screen is the startling change in IO bandwidth coming out of the impacted host. In this case, there's no changes being made at the impacted host themselves, but rather the congesting host, the overutilized host, is simply taking action to manage its profile and alleviate congestion across the fabric. Now, if this is a condition that is endemic, it's one that's a continuous congestion scenario, then the HBA is not fixing the problem, but it is managing the problem. So with a slightly lower IO profile, often that would not be noticed by the users of the system. It's not a huge impact to the IO on that system. And that system could be managed for days, weeks, or even months until there was a maintenance window and the IT team had a chance to either resize the workload or resize the hardware that that workload is running on. Alternatively, for something like a database operation, it may be a transient scenario where there is congestion for a period of time as a heavy load is being pushed across the fabric, or in a backup scenario, as Howard has described. And in that case, once that congestion event clears, then the host IO profile will return to normal operations. So it's not a scenario such as the past where you would change a queue depth and then you would permanently throttle the IO operations on that server. Instead, with this active congestion management, the IO profile will be changed during the congestion event. And when that congestion event has cleared, then that server will return back to its normal operations and be able to run unfettered as long as it was not creating congestion on the fabric. Now, looking at the link integrity example, in this case, it is actually the fabric that's detecting a flaky path on the link. So as Howard had described, this could be a link that has a bad cable or a bad connection where some traffic is allowed across the link, but periodically there's interruptions to that link. In this case, the switch would identify that that link is impaired and would send an FPIN-LI, a link integrity notification, to that specific port. Once again, that port then would forward that information up to the MPIO layer, and in this example, the Linux MPIO layer, and the Linux MPIO driver then being notified that it has a link that it shouldn't be using can fail that traffic over or move that traffic to an unimpaired link. Now, this is a very effective way of managing flaky links on the fabric. But one of the questions that does come up from time to time is, what if all of the links on an MPIO layer are impaired or flaky? Will the MPIO driver eventually turn off traffic? And the answer is no. The MPIO drivers are aware of the paths that have available to them, and they will continue to push traffic down a path, uh, any path that's available, and they will not today, at least, disable all of the available paths. So, to talk about using this from an HBA perspective, the question of if we want to use this capability in our fabric today, what is it that we would have to do? As Harsha has outlined, those settings are part of the fabric operating systems, and in many cases today they might be default settings. But the first step that you would want to do is review your fabric configuration and make sure that your fabric is set up to provide signals and notifications to the host devices. The second thing that you'd want to review if you're looking to enable the MPIO layer is confirm the operating system configuration. Once again, today, many of those operating systems will not be set up by default to recognize these signals. So you would need to configure your operating system to support the link integrity notifications. And then finally, from an HBA perspective, we are very well aware that our population of users is very conservative. So in many cases, the HBA configuration will not automatically take advantage of these new features, but there are configuration settings that you can set on those HBAs, and often those settings are configurable to allow you to be more conservative or more aggressive depending on how you want a particular server or port to react to these notifications. So with that information, I'm going to hand it over to Scott to talk about how storage will work in the congestion scenario.
Thanks, Dale. Yep. So yeah, this will be sort of more storage centric, but mimicking many of the thoughts expressed so far as well. So one of the kind of interesting angles here is the registration side. Maybe this is a little more interesting for storage. We tend to do a lot of updates non-disruptively, or things where you have an appliance that's there for a long time, and you might get this via code update. So one of the nice things about this technology is that, given some hardware assist, but even without any, you can actually implement most of this kind of FPIN support in software. And so you can introduce it in a code release and not have to necessarily replace a bunch of stuff. Of course, if you buy something new with the right code levels, you also get it. But it's notable in the storage space. Again, and it's not doesn't require user action to enable this. For the most part, that's true. It can, if you chose to do it that way. Maybe you want to be extra conservative, like Dale expressed. That happens too. But our experience has been that you can enable this for the most part, even if you don't enable maybe some of the active features. You can at least gain awareness, right? Reporting and logging and debug capabilities without any active user controls. Another thing to think about with this is it is a larger number of ports than typically maybe a host would see, and the array kind of has this opportunity to see a picture of at least some parts of fabrics with a little bit more information than an HBA would. Less than a switch, but it still sort of gives an interesting point of view that all the ports can see things happening based on what their zoning is and what their fabric connections are. And if there is support, again, this is part of that sort of automatic enablement part. The protocol allows, when you go to start discovering, you can send this out, and if a switch doesn't support it, it'll reject, and you'll find that out. If it only supports some features, you negotiate which ones. All of this can sort of happen as soon as this feature is enabled and loaded on the machine. So you sort of get a dynamic application and enablement of this feature set, and it can evolve over time as well, which is good. And then there typically will be some user configurable choices that have same defaults. Again, like Dale expressed, the same feeling we have in storage tends to be pretty conservative. So most of the time we won't enable an alert, something new, or an automatic change to throttling things without getting the customer first to choose to see those and do those things. Otherwise, it turns into surprise escalations and unexpected behaviors. So then, assuming that all is done right, it's registered and working. The first line of defense is reporting, right? Detection and reporting. So that's something that's sort of enabled by default. That's the one thing that's easy to enable without any risk is negotiating for it. And now you see them all, and you can log them, and you can log them to whatever sort of layers you need to. That's sort of before the level of alerting the customer, unless they've chosen that. But you can put it on, internal logs in the system, errors. You can put it up to application layers that are more like dashboards, and they're just available if people look. That kind of information. So that's the first line of defense in the storage space. So here's an example of one, sort of a mock-up of it, right? It's something in a command line space where you could see details about a link integrity event and the involved initiator port, some other details about it. The last screenshot there is a sort of a log of a couple events, and not looking at one specifically, but here's a history of some on this port. And then that can be expanded even further, and you can see the whole system at once, and get lists of kind of events that have happened and what they're seeing on different ports. So here's an example of a dashboard mock-up for that too. So that same information exports up through the various software layers to sort of the control planes and the application planes. And this is one that sort of captures the SAN health in general, and this is an additional view then that's FPIN centric to help give this sense of SAN awareness and SAN view. And you can look at each, and there are opportunities, right? This is something that can be implemented deeply with what you can do based off of these. This might just be informational to start and help an admin start to look into a problem, or it might trigger a manual mitigation step, or maybe it just compels over time to sort of get an awareness of this, so you could turn on automated remediations and still sort of see what's going on and how things are working. Next category here is the alerts. Again, another view of how that might look if you've got a history of these things, right? And these alerts can come to a view like this. Typically, they also go and turn into sort of like an email or some other dashboard event that's like a yellow flashing something somewhere for an admin to notice them, and that will compel action, right? Maybe hopefully a little bit preventatively. Once you see these things, it typically means there is some degree of impact, or there could be, but it may be before an application level detection of that, which is still preferable, right? So there's levels to that, right? It'd be nice to, ideally, you automatically detect and recover very quickly and prevent perceptible impact. But short of that, you may still get alert, get admins involved, and be able to debug and do something before applications are meaningfully impacted. So they're all kind of important steps in this process. So here's an example triage flow for one of these, right? This is B1 where there was actually application impact, where a customer felt something like performance, which is what we sort of face in the wild, without FPINs and in general. And it can be quite challenging sometimes to find it. But FPINs allow here where you've got a pretty clear indication. Maybe it does involve support personnel first, like maybe the array support folks do get involved, but you can see more quickly what the particular initiator port that's the peer congested port might be in this case, or if it's you even too, right? There's another signal there that says yes, it's your port, and you could start to isolate that and help figure out what the configurational problem is, or maybe what the profile problem is. All of this speeds the process. Even if you just have this detection level, it's much quicker to get to this point than without FPINs. And that's, this sort of, evidence can be reported back to, usually it's some admin or kind of escalation that's come that way, and that's who you're dealing with at that point. So here's an example mitigation process. This is in the congestion space, which is the one that's, again, the more pervasive problem I think we've faced. So in the case sort of like above, it was the peer congestion case. So that's where we're actually, as an array, sending data outbound, typically to initiator that's maybe oversubscribed itself. Maybe it has fan into it, or it's just asking for a lot of data, and the speeds are mismatched, which is a common problem, right? So the first thing you might do, once you identify that, you might look and say, okay, one mitigation is if there's speed mismatches, you could try to resolve that via hardware change, right? So there could be a reconfiguration of those initiators. You can implement throttling on those too, as Dell expressed, but this is sort of more from the storage or the admin point of view. And then another is the throttling part, right, which is interesting, kind of dynamic here. There's a couple different layers to this. They're sort of available generally. One is kind of available to any implementation if they want, any software, because it's sort of a software thing to do this at the ULP level, at the IO level. So say it's SCSI and you get commands in, you actually have kind of control about when you return the data, right? You could actually add a delay. You could implement a delay to say this particular initiator can't take more than a certain pacing of IO, where you know the size and you kind of calculate out that bandwidth and you can pace that. It does have the weakness though of that it bursts at line rate. So you're still controlling the overall bandwidth, but you're not able to tune the instantaneous frame rate out of the chip onto the wire, because it's still running at its maybe 2x line rate of what that initiator can receive. So then the next one comes into play, and this one does require hardware support. So this is that frame level throttling, and it typically needs to be at connection specific frame level throttling to be useful in this space, right? Where you just want to target a particular initiator that's overloaded. And there's varying speeds too, so you can't set them all to the same speed. So that requires some hardware support, but it does mean you get a more successful and basically zero congestion situation, excluding fan into the host where it sort of has too many things coming into it from all different directions. But this one can help at least with that. And you could actually frame rate lower than the max of that if you see other congestion happening. So you can dynamically do this even more aggressively and help alleviate that pressure. And so that last bullet there is for the application part of this. Again, it could be manual. That's sort of the first generation of things, probably, right? You wouldn't turn this on unless a customer said, okay, yes, let's turn this on. And you could start doing that, maybe for this particular case. And then the next stage of that is automatic, where maybe that customer says, okay, there's been enough of this, but we've kind of proven it works. We're comfortable now turning on a broadly automatic mode where the software can respond and tune these things. And it's sort of been proven. I did want to touch on the opposite direction because it happens too, right? So if the target is overwhelmed, which is very common too, because we don't have a lot of control over the inbound IO rates, the initiators kind of make that decision, and you might be fanned in from many. But there are some things you can still do. So for inbound data is write data typically, so you can, thanks to the FC protocol having some handshake there, there's a way to flow control at the IO level by delaying again and maybe holding off a little bit. And maybe you naturally do this because you're overloaded. And then the next is that you can rebalance your compute. That's another one that's possible, maybe dynamically, but maybe again, it's manual depending on the situation. But you could maybe aim more, cores at this port. And the last thing is sort of to tune configuration, like environmental configurations too, right? You could add more ports into the group that these initiators are aiming at, that load balances. You can isolate maybe a really, heavy batch or a heavy like database job to a particular port and have it not deal with anything else, or isolate it in the fabric a little better. And there's some things you can tune there as well. So the last thing I wanted to touch on was some growing pains, the challenges, right? This was mentioned a little bit by Dale too and others. Mostly it has been just the evolution of these features and the getting the proper hardware support and firmware levels into switches and HBAs and the arrays and configuring it as it evolved. So your labs tend to sort of dynamically go through stages and have a lot of mixed modes as you go through them all. So that was something that's a big challenge sort of as in terms of deployment, but over time it gets easier and everything starts to have all the right stuff as your data center evolves. It becomes a much easier process. All right, I guess I'll pass back to Erik.
Thanks, Scott. So just to summarize what we just reviewed, we had a fabric notifications overview from Howard, and he went into some congestion use cases, and then Harsha, Dale, and Scott walked us through the different implementations and considerations. And we are running low on time, so just to get through the rest of the slides that I think you need to see, there are some solution level detail if you want to understand where these features that we just discussed are available. This is just provided for reference, so we don't have to drain this slide. And then there has been a tremendous amount of information already published on this topic, and highly recommend that you go out and take a look at this. Again, the slides are available for you to download, and you can click on these links and be able to get more information. And if there's any questions in the last 2 minutes, feel free to ask. You can also just enter the question, even if we might not have a chance to get to it, and we will, like I said, respond with a Q&A blog post after. So, you can do that now, or if there's a question, please feel free to type it in. I don't see anything. But all right, so we'll leave it there. If you do have questions after and you wanted to reach out, I mean, this will be published, the announcement for this session will be published in a number of different ways. Feel free to reach out. My email is eric.smith@dell.com. You're free to send me an email and I'll respond, as will any of the presenters. So with that, I just ask that you, before you leave, please rate the webinar and provide us with your feedback. And again, the slides will be available there, and you can, and we'll be posting a Q&A. I think we've got a couple of questions that we can respond to. And with that, thank you for your time.